Hi everyone, I'm Jim Carroll with Converge Digest and NextGenInfra.io. Just a month ago in June 2025, I spoke with Pete Vecchio of Broadcom about the launch of Tomahawk 6, their next generation Ethernet switching silicon, and the first to break the 100 terabit per second barrier. That conversation, and the link to that video is in the description below, focused on the shift towards Ethernet as a unified fabric for AI and the cloud. And our discussion covered everything from Broadcom's cognitive routing 2.0 to co-packaged optics and scale-out cluster topologies. So today, we have Pete Vecchio back once again to dive into another topic or another side of this whole AI data center equation, and that is the scale-up networking fabric that's needed. And Broadcom is now launching Tomahawk Ultra. In many ways, this represents a rethinking of Ethernet for tightly coupled accelerator clusters. It's Broadcom's Scale Up Ethernet, or SUE, which promises to deliver sub-microsecond switching, truly lossless transport, and in-network collective operations. So with that, welcome back, Pete. Good to see you again.
Good to see you, Jim. Thanks for having me on again.
So first, let's jump into it with an overview of what is Tomahawk Ultra and how does it differ from the Tomahawk 6 that you guys just introduced?
Okay, sure. Yeah, so I think as you mentioned, this is really a groundbreaking switch. This is a first for the industry. I think it shatters a lot of misconceptions that people had about Ethernet switches. We started on this architecture a little bit over 3 years ago. And at the time, we were looking at the roadmap we had for our switches, trying to figure out, are there certain application areas where we might want to focus, specific, very dedicated silicon. And what we saw was that, there's some applications for high performance computing at the time, where there were some switches, notably InfiniBand played, in that space, where they had an advantage as far as latency, as far as packets per second. And it wasn't so much because of the benefits of the protocol. It was really the design choices that were made for that specific application. So that's the point we decided that we wanted to have an Ethernet switch, which is focused on HPC and also on high performance, AI networking. And that's where we came out with Tomahawk Ultra. So this is a, very, very low latency. So it's 250 nanoseconds, at 51.2 terabits per second. And at that very high bandwidth, we can still stream minimum size frames. That was really one of the misconceptions people had about Ethernet, was that you could not achieve that low latency and at the same time also be able to stream these minimum size frames at a very high bandwidth. So what we've done here is, I think we've shattered these misconceptions. We've reimagined what an Ethernet switch is. We have something that is really focused on HPC and AI scale up.
Okay. So why does that matter for AI clusters? Why this emphasis on the latency?
Well, I'd say especially for AI clusters in scale up and scale up in particular for inference, that the latency tends to be very important. There are also some features that you'd like to have in a switch which is tuned towards scale up that we've added to Tomahawk Ultra that allow you to have very lightweight interfaces on the XPUs. So in particular, with a scale-up network, the way that's going to differ from other networks is that, the topology is very simple. It tends to be a single hop. So you have an XPU talking to a switch, talking to another XPU. And also the interfaces from those XPUs might be very, very high bandwidth. So you might have, these days, 10 terabits, on the order of 10 terabits per second of bandwidth coming out of an XPU talking to that switch. So it's very important to have the functionality on those XPUs to be as lightweight as possible. So you want to have, the transport, the interface to that external networking interface to be, as lightweight IP, so as small in the silicon area and as low in power as possible. So there's some features that we've added to Tomahawk Ultra to make that network, very low latency, but also lossless. And that allows you, that lossless behavior allows you to have these very lightweight interfaces on the XPUs. So I think that
Okay.
combination, that lossless behavior, plus that very low latency will give you much better performance for applications, in particular, inference for AI training and an inference that is a much more important factor for those applications.
Okay, and how does that compare with other approaches that are out there, NVLink or InfiniBand, which you mentioned just now?
Yeah, so I think primarily, I mean, the first thing is that this is Ethernet. It's standard. You can use like all the tools that you have today for Ethernet. You have the whole Ethernet ecosystem. Um, it is something also where it is very very low latency at a high bandwidth. There's no switch, no scale up switch that equals what we have for Tomahawk Ultra as far as bandwidth. And we don't know what latency they can achieve, at this bandwidth. So we can achieve the latencies at a high bandwidth that are going to be comparable or better than any other scale-up networking technology. So the scale, for example, like the number of XPUs you can connect in a single hop with a Tomahawk Ultra is over 3x the scale of what you can do with an NVLink switch. So you can have a much larger scale-up domain.
Okay, and does this unlock other capabilities for the AI model training then?
Well, I think it's about efficiency. It's basically the fact that you can keep those XPUs running as efficiently as possible, less time waiting on the network. It also allows you, because we have this the ability to have these very efficient interfaces to the network. It allows you to have more area, more power on that silicon for the compute engines. So, it's basically a combination of, standard Ethernet technology at very high performance and also allowing for a very lightweight interface on the XPUs. Also, I mean, with this low latency and those lightweight interfaces, we can achieve an application layer to application layer latency, from one XPU to the other of about less than 400 nanoseconds. So the capabilities you're unlocking are just more area that you can dedicate to the compute engine and just much higher efficiency as far as being able to transfer data between those XPUs.
Okay, could you tell us about the concept of the in-network collectives?
Yeah, sure. So I mean, a collective operation, where that comes into play is the GPUs tend to operate on a parallel processing task. They're all doing it in parallel. They'll have an intermediate result, and then they need to pass that back and forth to other XPUs. So one example would be an AllReduce, where you have an intermediate result. You need to take the results from all the XPUs. You need to combine it together, take an average, and then propagate that out to all the XPUs. So if you didn't have something that was in the network, what you would do is you would copy data from XPUs through the network to other XPUs, and then do the averaging on those XPUs and send it back and forth across the network. I mean, here for that AllReduce example, what you would do is all the XPUs would talk to the INC, that in-network collective engine that we have on Tomahawk Ultra. So it'd be like one data transfer into the switch. The switch would do that AllReduce operation, and this could be a floating point, it could be an integer operation, and then it would propagate the results outward. So you have two benefits. One is that you have some of the compute, that collective, that AllReduce computation being offloaded to the network. And probably more importantly is that you are saving on network bandwidth, that you're doing one transfer into the network, you do the AllReduce there, you propagate the data outward, rather than have to bounce the data back and forth between the different XPUs.
Yeah, it's getting quite sophisticated, isn't it? It's
Yeah.
not just the Ethernet that we've all known. This is something a lot more advanced. So, could you tell us about Broadcom's overall vision and strategy with the scale up Ethernet and now SUE-Lite?
Yeah. So I think it was a couple of months ago we published the SUE spec. We contributed that to OCP. It's freely available on the Broadcom website. And the idea there is that we work with a lot of XPU designers that know the computation, they know the processing elements very well, but they might not have a good idea of like how do they take the data and transfer it most efficiently across the network. And also, how do you do that with Ethernet? So the idea behind SUE is to show that, with standard Ethernet, what is it you can do on your XPUs to efficiently pack the data, to transfer the data, and to handle the transport between the XPUs. So, that SUE framework is basically saying, if you want to use standard Ethernet, here's how you can implement that on your XPU in a very efficient way. because again, one of the misconceptions about Ethernet is that it is very heavyweight. And if you're operating in a global data center network, that interface for that Ethernet interface might be fairly complex. But if it's just in that simple topology, transferring data between the XPUs, it can be very, very lightweight, very simple. So the idea behind SUE was, here's a functionality you can implement, on your XPUs and wind up having very, very good networking performance. SUE-Lite is new, and the idea there is it really depends on what sort of capabilities you want to have between the XPUs. So, for example, with SUE, we have reliable transport from end to end, so from one XPU to another XPU. So one XPU would send the data, and then the receiving XPU would send something back to the sender and said, yes, I reliably, I got accurate data from you. So with one other strategy is you could just handle things at the link layer. So for example, in between link partners, you could say on a packet by packet basis, was that packet efficiently transferred? So that's one difference. One of the differences we have between SUE and SUE-Lite is reflect what sort of transport model, what sort of error model that you have in the network. There's some other capabilities about how you pack data, but the idea is that we give you some options then really depending on what sort of transport, what your memory model looks like, what sort of reliability model you want to have for your scale-up network.
Okay, and so the overall architecture or the data center vision here, I guess we're in this case it's the scale up for AI clusters that you're talking about, but you still retain the capabilities with Tomahawk for the more traditional data center east-west spine leaf data centers that people have been building, right?
Well, I'd say, so the packet processing is not quite what you'd have, say, in a Tomahawk 6. In order to achieve that low latency, we really had to focus it on this, this one particular application. So are you going to get all the VXLAN and all the complex tunneling and MPLS functionality you'd have in a general data center networking switch? No, but you don't need that for HPC. You don't need that for scale up. So what we've done here is really said, for HPC and for scale up in particular, what are the protocols? What are the table scales? What's the buffering that you need? That's one other difference that you'd have is that, in a global data center network, you're going to have congestion. You're going to have larger packet buffering. In a scale up network, it's a single hop, and also you want that to be low latency. So you're going to have good congestion control, within that network. And you don't want to have large buffers because if you have large buffers, it basically means you'll have queuing delay. And it's really self-defeating that you're trying to achieve low latency. So I'd say, there are significant differences between the pipeline, the packet processing, the traffic management capability that you'd have in a Tomahawk Ultra class device as compared to, say, a Tomahawk 5 or a Tomahawk 6.
So, Pete, what are some of the advanced features in Tomahawk Ultra?
So, if you look at the SUE spec, there are a few things we bring out that you'd like to see in a networking switch to really make it optimal for that scale-up application. One of them is going to be low latency, of course. So that is something we've achieved with that 250 nanosecond latency on Tomahawk Ultra, which is half or a quarter of anything else on the market. So we've achieved the low latency. Second thing would be lossless behavior. And so that lossless behavior is enabled through link layer retry and credit-based flow control. So those were outlined in the SUE spec. Those are included in Tomahawk Ultra. And the fourth thing is that you'd like to, in some cases, depending on the size of the transfers, the data transfers between the XPUs, you might want to minimize the overhead on the wire from the headers. So standard Ethernet frame, you could have up to, say, 46 bytes, even for IPv4, just dedicated in the headers. Minimum size Ethernet frame is 64 bytes. So that 46 is a good chunk of the total usable bandwidth. So one thing we outlined in SUE is that we show you how you can have a header on the order of 10 bytes. So that allows you to have much better efficiency for those data transfers on the network. So really all the things that you want to have that we outlined in the SUE spec, all the things you'd want to have for a scale-up network, those are all included in Tomahawk Ultra.
So Pete, how does this fit in with other advancing standards that we've seen, like UA Link?
Mm-hmm. Yeah. So I think, first off, we've achieved what some of those specs aspire to do, and some of their design targets. We've achieved that today with Tomahawk Ultra. So, one of the notable specs out there, I mean, their target for a chip with 512 lanes is 300 nanoseconds, and that's a target for a chip that doesn't exist today. Can they actually achieve it? We don't know. But for example, we do see that we have customers and already, like very large customers that have publicly announced that they'll be taking their future protocols, for scale up and tunneling them over Ethernet. So, if you wanted to have, some proprietary or some, standard that's under development, you wanted to be actually, use that today, you can tunnel that today over Tomahawk Ultra.
Okay. All right, great. So, Pete, what's next in terms of bringing Tomahawk Ultra to market, deployment strategies, and kind of market rollout?
Yeah. I mean, what's going to be interesting here is that we do expect a super rapid rollout of this switch. One thing we point out is that this switch is 100% pin compatible with Tomahawk 5. So what that allows you to do is like all the OEMs and ODMs that have designed systems around Tomahawk 5 can drop in a Tomahawk Ultra and just leverage all the design they have and all the qualification so they can immediately offer a new platform for a new market. We've also made it that we have a unified SDK. So if you have software for the previous generation, then there are some new features. For example, to support HPC, we have this topology-aware adaptive routing, and that's a new feature that we have in Tomahawk Ultra. So there'll be some new APIs, so some software changes for that. But in general, most of your software will be applicable from what you have with say a Tomahawk 5 or Tomahawk 6 to Tomahawk Ultra. And the hardware is basically it's almost 100% compatible. You can just drop in a Tomahawk Ultra. So as far as path to market, there's the hardware and software easy migration. SUE was designed to be usable with any Ethernet switch. So if you whether you use SUE or SUE-Lite, you can use a Tomahawk 5, you can use Tomahawk 6, or a Tomahawk Ultra. So a lot of flexibility and very rapid time to market for this product.
All right, great. Sounds like a lot's cooking, and it's good to see the semiconductor and the systems and hardware guys keeping up, or at least trying to keep up with all those crazy pace of innovation for the model developers.
Yeah, thank you, Jim. It was good talking to you.
Yeah, good talking to you again.